Good evening, everyone, and may the 4th be with you. Thank you, Mr. Vandenberg. Did you guys at least remember that today is Star Wars Day? So I see class participation is extremely low this evening. So I assume it's due to the 2 semester tests that's being written tomorrow. That explains it. So, few points of admin. What do you mean also this dropped cause 151 on you? Okay, I understand. Ish, okay, so I'm with you 8 a.m. tomorrow. What do you need to do for the assignment? Abstract data structures. That is very fun. Data structures was one of the modules I disliked the most in my undergrad. So from my side, I have 2 points of admin. The first one is I have received a few emails since last night asking what is the 0% they got for class participation. Just to clear that up, on Blackboard Collaborate, there's no function where I can check for class participation. So unfortunately for class participation, I need to assign a mark and just to have statistics and generated class list of who is attending these sessions. I need those statistics for the department to check if anyone is struggling, anyone has data problems, connectivity problems, device problems, where things went wrong in a semester. So I'm not going to use these marks. It's primarily going to be used as class list to check who participated in these lectures. So that's the one thing for you guys to remember. So don't panic and think I gave you zero for your participation. I'm just actually using it for statistics. And then secondly, I've received, so how many more lectures do we have? We are now halfway through the lectures. So looking at my lecture slides and planning we are now tonight on lecture slide 10, and we have 21 lecture slides. So we are halfway through our lecture material. So don't worry. And then I've received also a few emails. So let me just open up the notes. I can perhaps share my screen as well. Uh, so let me see if I can share. I can share my screen, share the tab. So just going to open up the web page. Okay, I got it. So let me share my screen. So can everyone see the screen? Okay, awesome. So I've received a few emails saying the moon went behind the horizon or behind an obstacle when observing, and got asked when would I recommend to restart the observations for those that is struggling. So I've looked at this website. If you just Google moon rise and set times, I'm in Johannesburg, so that's my location. Between Johannesburg and Pretoria, there won't be any difference. But between Johannesburg, Pretoria, and Durban, there will be differences, and Bloemfontein will be differences, and in Cape Town will be differences. So this is a nice interactive graph. So currently we can see to where the moon is. So currently we see the moon is sitting at already 20 to 2 the afternoons. Then this will be below the horizon. We can see it in the daytime now. So I would recommend starting our observations, or for you guys to start new observations on the 19th. And I would recommend you do it at 9 o'clock the evening, because remember now at 9 o'clock the evening, you will have an altitude of 33 degrees, so that will clear most trees and buildings. And the moon will be sure it will be visible at 9 o'clock. But going on to the next day, the 20th, going to 9 o'clock, we'll see the moon is a little bit higher, now at 44 degrees, still visible. Going 10 days into observation, so the 29th, shows the moon is rising at 8:30. So you will still be able to see it at 9 o'clock. You can even move it up to 10 o'clock, just to be sure. So let's say 11 o'clock, it's at 30 degrees. That's actually not bad. So let's go back to the 19th. So here it's setting already. So let's say at 10 o'clock. So I would pick my observation time the 19th between 9 and 10 in the evening, and I will stop the observations on the last observation time will then be the 29th. And I would suggest doing it between 9 and 10. And with this, you'll still get your full moon and a few of the moon cycles. So this will be my advice for you guys redoing the observations. So on 9 o'clock, the moon is too far for a clear observation. So it depends on your location. So you can play around with this data. So what is the chance of rain? I have no idea what the chance is of rain. So that is something you have to investigate yourself, but this will be my best advice. So if we experience clouds, can we still take the picture and still draw the moon where it has to be according to Starwalk? Yes, you're welcome to do that as well. Pleasure. So for tonight's lecture, we are going to start looking at the formation and structure of stars, how stars gets formed, what's happening in the inside processes of stars. So I want to ask you guys a question. So since yes, Mr. Levuyo.
So before you carry on, so I just wanted to ask, so what is the difference between a particle physicist and a chemist?
Okay, so a chemist will primarily look at molecular bindings and the chemistry behind everything. But a particle physicist looks at pieces of material that is smaller than molecules. So then you start looking at what is a molecule. So a molecule will consist out of electrons, protons, neurons. What does electrons, protons, and neurons consist of? That will consist out of charms, quarks, up quarks, down quarks, strange quarks, charm quarks. And what are quarks made out of? Yes, Mr. Levuyo.
Oh, sorry, sir. That was a mistake.
No problem. So chemistry literally look at chemical bindings, where the smallest they look at is molecules. Particle physicists look literally at the fundamental particles that is put together to create everything that we know. And I hope that answers your question.
And so, are these particles like what particle physicist researches it like fundamental forces, like what is magnetism and like what makes up electricity, like things like that.
Yes, particle physicists will investigate those forces, but the biggest particle experiment in the center going on is CERN with a Large Hadron Collider. So if you're interested of what makes atoms stick, that is where particle physics comes in. And also a branch of particle physics that's being extremely investigated is string theory.
Thank you, sir.
It's a pleasure. So last night I discovered how to play videos through Blackboard Collaborate. So tonight I wanted to show you another video, but just to make sure before I play, does it make any difference to you guys' bandwidth? Because I've been thinking I've been slow showing slides, I've been putting on my camera, I've been lecturing, so there shouldn't be much of a difference of me lecturing and playing a video. So would you guys like me to show a video of what we'll be discussing this evening? Okay, so let's do it. So let me find the video. Just going to open it up on my side. So there's actually, so this is going to be really cool. I hope you guys is going to enjoy it. So let me share my application screen. Does anyone have video and sound?
Stars in the sky look pretty, flickering intense diamonds dotting the velvety night. But make no mistake, they are churning cauldrons of violence, barely constrained thermonuclear generators, creating enough energy to vaporize the Earth 1,000 times over. Their lives depend on it. Heck, our lives depend on it. But in their case, how they live and how long they live depends on that creation of energy. And in this universe, nothing lasts forever. Very roughly speaking, we can divide stars into two groups, low mass stars and high mass stars. That line lies around 8 times the mass of the sun, and the reason for that is something we'll get to shortly. Things get very exciting at the high end, but for now, let's take a look at the low mass end of the scale. Things are simpler there. Stars make energy in their cores by fusing hydrogen into helium. This is actually a pretty complicated process with lots of steps, but in the end, 4 protons plus some other ingredients get turned into 1 helium nucleus. Each time this happens, a little bit of energy is released, but in the core of a star, it happens countless times every second. It adds up to a lot of energy, enough to power a star, in fact. The rate at which hydrogen fusion occurs depends on how much pressure the star has in its core. A higher mass star squeezes hydrogen harder, so it fuses far more quickly. The rate is so much higher, in fact, that even though they're a lot bigger than low mass stars, high mass stars run out of hydrogen fuel in their cores more quickly. The lower mass a star is, the longer it lives. In the lowest mass stars, cool red dwarfs, the rate is so slow they last a long, long time. But there's more to it than that. They fuse hydrogen only in their very centers, and their cores aren't very big. Outside of this small region, the gas is convective, which means the hot stuff rises all the way to the surface, cools, then falls back to the core. That's important, because it means the entire star is available for fuel. Both hydrogen and helium rise up through the star and then fall back down. The star can't fuse the helium, but the hydrogen that makes it back to the center is just more grist for the mill. Even after a long, long time, these stars can still shine as the hydrogen mixed throughout the star eventually makes it down to the center. So how long can a really low mass red dwarf last? 1 trillion years. 1 trillion! The universe itself is less than 14 billion years old. So even the oldest red dwarf stars are basically infants. They're just barely getting a start in life, and they'll look pretty much the same for the next, 990 billion years or so. Eventually, though, they do run out of fuel. When one does, the star itself will be nearly pure helium, plus whatever heavier elements it was born with, and fusion will cease. It'll then cool, which will take many more billions of years. Finally, it'll be a cold, black, dead star, and for them, that'll be pretty much that. Or so we think. The universe is far too young for any of these red dwarfs who have run out of fuel yet. That's true for stars at the lower end of the mass scale, up to roughly 1/3 of the mass of the sun. But stars with more mass than that, stars more like the sun itself, work a little differently. Their cores are bigger and hotter and denser. The different conditions inside them means the material in them doesn't convect. The hot stuff doesn't rise away from the core. What's in the core stays in the core. Outside the core, there's a very deep and active convection zone, but that doesn't interact with the material in the core itself. This means that not only do stars near the sun's mass use up their fuel more quickly than red dwarfs, they have relatively less fuel to work with as well. Depending on their mass, their lives aren't nearly as long. For the sun, that total lifespan is about 12 billion years, give or take. The sun is nearly 5 billion years old now, so it's approaching middle age. Its life is similar to other stars of similar mass. So let's take a look into the far future. Will our sun go gently into that good night? Ever since the sun was born, it's been fusing hydrogen into helium in its core. The helium is trapped there, unable to be used as fuel, and it's building up in the core like ash in a fireplace. As it does, the density in the sun's core slowly increases. When you compress a gas, it heats up. That means every day, the sun's core gets a wee bit hotter. That extra heat works its way out through our star, heating up the outer layers too. A hotter gas shines more brightly, so the sun has been steadily increasing in brightness too. It's an incredibly slow but inexorable process. The sun's increased in luminosity by about 40% since it was born, and it's not done. Helium is still building up in its core, and eventually it'll run out of hydrogen to fuse. Without fuel, fusion in the core will stop. Helium can be fused into carbon and a little bit of oxygen and neon, but it has to be incredibly hot to do so, and the sun's core won't be anywhere near those conditions. Still, half the sun's mass is bearing down on the core, so even though fusion stops, the core will continue to contract and heat up. It'll get so hot that the temperature outside the core will get to hydrogen fusion temperatures. Like igniting a match by holding it near a flame, the hydrogen outside the core will start to fuse. That'll occur in a shell surrounding the core, adding its heat to the outer layers of the sun as well. When you heat a gas, it expands. The sun's outer layers will do just that, and our star will grow to well over twice its current size. Astronomers call a star like this a subgiant. Not only will it grow, but its color will change. The sun will be giving off more total energy than it does now, but its surface area will increase so much that the amount of energy radiated per square centimeter will go down. There'll just be a lot more square centimeters. This means, ironically, that the surface will actually cool. The sun's temperature will go down. Cooler stars are red, and so the sun will be too. But the core still isn't done. The details are complicated, but the core continues to contract and heat up. It gets so hot that the outer layers swell even more, and the sun can bloat up to a fantastic 10 to 150 times its present size. It will then be a red giant. Red giants are fantastically bright because of all the energy percolating up from their interiors, coupled with their enormous size. When it turns into a red giant, the sun will increase its luminosity by an incredible 2,000 times. That huge increase in luminosity does more than just make the sun bright, though. As a red giant, the sun will be so swollen that the gravity at its surface will drop substantially as it is now. The force of gravity holding it down is weak, but the force from all that light blasting out from below is strong, easily overpowering gravity. Material on the surface will get blown off like a leaf in a hurricane. Think of it as a super solar wind. That means the sun will shed mass a lot faster than it does now. While it's a red giant, it'll lose fully 1/3 of its mass. At some point, the core contracts and heats up so much that the conditions will finally be primed for helium fusion. Suddenly, helium is converted into carbon, releasing a lot of energy. In a weird twist, due to a lot of very complicated physics, the The core itself winds up expanding, absorbing most of that energy. In the end, less energy is pumped into the outer layers, so the sun's outer layers contract. The sun shrinks. The outer layers get dense again, which warms them up a bit, and the sun turns from red to orange. It's still pretty big, more than 10 times its current day size, and puts out 20 to 50 times as much energy as it does now. But then we see a sort of reboot of what's happened in the core before. This time, though, helium is fusing in the core, and the carbon is building up like ash. Once again, the core starts to contract and heat up. This dumps more energy into the outer layers. They expand and cool, and the sun turns into a red giant again. This time, it's even brighter and bigger and loses even more mass, shedding over half of what's left. In the meantime, helium fusion isn't very stable, to say the least. It swings wildly, increasing and decreasing its rate by huge amounts on very short timescales. The sun will probably undergo a series of tremendous paroxysms, epic eruptions as the helium fusion spikes, creating huge surges in energy production. It'll lose even more mass each time. Finally, though, we approach the end game. The sun doesn't have enough mass to squeeze carbon atoms enough to fuse them. They build up in the core until there's no more helium and fusion stops. On top of that, well, there's nothing on top of that. By this time, the sun will have literally blown off all its outer layers. It's essentially a naked core, a hot, intensely bright, super compact ball, not much bigger than Earth. We call this a white dwarf. Its fate is sealed. It can't generate energy, so it'll cool and fade over the next few tens of billions of years. At that point, we can safely say the sun is dead. But that's not always the case for all stars. Some with more mass than the sun still go through another phase before dying. They form what are called planetary nebulae, and these are so amazing and beautiful that they rate their own episode, which, along with more fun stuff about white dwarfs, we'll get to next time. So that's it for the sun. But what about us? Of course, the Earth won't fare very well during all this. It'll get cooked before the sun even becomes a subgiant, and by the time the sun is a red giant, we'll be good and fried. The average temperature on our planet will be, and in a sense, it'll look much like it once did so many billions of years before, when it first formed, a molten ball of rock. But it gets worse. When the sun expands, it'll reach a radius very close to the size of the Earth's orbit now. Does that mean our planet itself will be consumed by the sun? Maybe not. As the sun expands, remember, it loses mass. That means its gravitational pull will weaken, and Earth will move out from the sun into a bigger orbit. If things work out right for us, the Earth will back off faster than the sun expands, and we'll avoid finding out what it's like to be inside a star. Due to a quirk of physics, if the sun loses more than half its mass, its gravity will decrease so much the planets will no longer be gravitationally bound to it, and they'll be flung into interstellar space. I'm not sure that's any better for us. Either way, the Earth will have been long dead, and hopefully humanity will have figured out the trick to interstellar travel by then. All those Earth-like exoplanets around younger stars will look pretty nice in a billion years or two. Mind you, this isn't happening anytime soon. The sun won't become a subgiant until it's nearly 11 billion years old, over 6 billion years from now. The first red giant stage happens when it's over 11.5 billion years old, and the second stage a half billion years later. This is a long, long time coming. If the sun had more mass, it could avoid this fate. A star with about 8 times the sun's mass can. It has enough mass to squeeze those carbon nuclei hard enough to fuse them together. Those high mass stars have a much different and far more explosive fate than lower mass stars like the sun. And trust me, we'll cover that in lots of fun detail soon. And while this all sounds very bleak, not all is lost. This is all part of the natural cycle of the universe. And in fact, we wouldn't be here at all if it weren't for the way stars live and die. Be thankful for what you have, and that we can not only observe it, but understand it too. Today you learned that very low mass stars live a long time.
So that's the first video we was going to watch. I'm going to show the second one on high mass stars, but I see 2 questions. So are those gamma signs photons getting released? Yes, that's photons getting released. And then after tonight's class, I will upload the new lecture slides. So I'm going to share my application screen again.
Stars are in a constant struggle between gravity trying to collapse them and their internal heat trying to inflate them. For most of a star's life, these two forces are at an uneasy truce. For a star like the sun, the balance tips in its twilight years. For a brief, glorious moment, it expands, but then blows away its outer layers, leaving behind the gravitationally compressed core. It goes out with a whimper. Well, a whimper from a 2-octillion-ton, barely constrained, nuclear-powered fireball. But more massive stars aren't quite as resigned to their fate. When they go out with a bang. A very, very big bang. In the core of a star, pressure and temperature are high enough that atomic nuclei can get squeezed together and fuse. This releases energy and creates heavier elements. Hydrogen fusion makes helium, helium fusion makes carbon, and each heavier element, in general, takes higher temperatures and pressures to fuse. Lower mass stars like the sun stop at carbon. Once that builds up in the core, the star's fate is sealed. But if the star has more than about 8 times the sun's mass, it can create temperatures in its core in excess of 500 million degrees Celsius, and then carbon will fuse. There are actually a lot of steps in this process, but in the end you get carbon fusing into neon, magnesium, and some sodium. What happens next harkens back to what we found goes on in the sun's core as it ages. Fuse an element, create a heavier one, then that heavier one builds up until the core contracts and heats up enough to start fusing it. So carbon fusion makes neon, magnesium, and sodium, and those accumulate. The core heats up, and when it reaches about 1 billion degrees, neon will fuse. Neon fusion creates more magnesium as well as some oxygen. These build up in the core. It shrinks, heats up to about 1.5 billion degrees, and then oxygen fuses, creating silicon. Then that builds up until the temperature hits about 2 to 3 billion degrees, whereupon silicon can fuse. Among a pile of other elements, silicon fusion creates iron, and that's trouble. Big, big trouble. Once silicon fusion starts, the star is a ticking time bomb. But before we light that fuse, let's take a step back. What's happening to the outer layers of the star? What do we see if we're outside, looking back at it? Because the star was born massive, it spent its hydrogen fusing days as a blue main sequence star. Stars like this are extremely luminous and can be seen for tremendous distances. Like the sun, though, a massive star changes when hydrogen fusion stops. Its core contracts, and then helium fusion begins. It swells up just as the sun will, but instead of becoming a red giant, it generates so much energy, it becomes a red supergiant. These are incredibly huge stars, some over 1 billion kilometers across, and they are luminous. For example, Betelgeuse in Orion is a red supergiant and one of the brightest stars in the sky, despite being over 600 light years away. From that distance, you need a decent telescope to see the sun at all, and that's nothing compared to VY Canis Majoris, the largest known star, which is a staggering 2 billion kilometers across. We even have a special term for it, a hypergiant. As the core switches back and forth from one fusion reaction to the next, the outer layers respond by contracting and expanding, so a red supergiant can shrink and become a blue supergiant. Rigel, another star in Orion, is a blue supergiant, putting out over 100,000 times as much energy as the sun. Okay, let's go back to the core. It now looks like an onion with multiple layers. Iron is building up in the center, surrounded by fusing silicon. Outside that is a layer of fusing oxygen, then neon, then carbon, then helium, and finally hydrogen. You might think massive stars would last longer because they have more fuel than lower mass stars. But the cores of these monsters are far hotter and fuse elements at far higher rates, running out of fuel more quickly. A star like the sun can happily fuse hydrogen into helium for over 10 billion years. But a star twice as massive as the sun runs out of hydrogen in just 2 billion years. A star with 8 times the sun's mass runs out in only 100 million years or so. And each step in the fusion process happens faster than the one before it. In an extreme case, like for a star 20 times the mass of the sun, it'll fuse helium for about 1 million years, carbon for about 1,000, and neon fusion will use up all its fuel in a single year. Oxygen lasts for only a few months. Silicon fuses at a ridiculously high rate. The star will go through its entire supply in, get this, a day. Yes, 1 day. The vast majority of a star's life is spent fusing hydrogen. The rest happens in the metaphorical blink of an eye. Silicon fuses into a bunch of different elements, including iron. That inert iron builds up in the core, just like all those elements did before, And just like before, the iron core shrinks and heats up. But there's a huge difference here. In all the previous fusion stages, energy is created. That energy transforms into heat, and that helps support the soul-crushing amount of stellar mass above the core. But iron is different. When it fuses, it actually sucks up energy instead of creating it. Instead of providing energy for the star, it removes it. This accelerates the shrinking, compressing the core, heating it up even more. Even worse, at these temperatures and pressures, the iron nuclei suck up electrons that are whizzing around, which are also helping support the core. It's a double whammy. Both major means of support for the star are removed in an instant. Silicon fusing into iron is happening so fast, this literally takes a fraction of a second once it gets started. The core gets its legs kicked out from under it. It doesn't shrink, it collapses. The gravity of the core is so mind-bogglingly strong that the outer parts crash down on the inner parts at a significant fraction of the speed of light. This slams down on the central core, collapsing from several hundred kilometers across down to a couple of dozen kilometers across in just a few thousandths of a second. The star is doomed, because all hell is about to break loose. Now, at this point, one of two things can happen. If the star has less than about 20 times the sun's mass, the core collapse stops when it's still 20 or so kilometers wide. It forms what's called a neutron star, which I'll cover in the next episode. If the star is more massive than this, then the collapse cannot be stopped by any force in the universe. The core collapses all the way down to a point. The gravity becomes so intense that not even light can escape. A black hole is born. We'll cover black holes in a future episode as well. But for now, what happens when the core collapses and suddenly stops? The core of the star, whether it's a neutron star or a black hole, is now extremely small with terrifyingly strong gravity. It pulls on the star's matter above it hard. This stuff comes crashing down at fantastic speed and gets hugely compressed, ferociously heating up. At the same time, two things happen in the core. While this stuff is falling in, a monster shockwave created by the collapse of the core moves outward and slams into the incoming material. The explosive energy is so insane, it slows down that material substantially. The second event is that the complicated quantum physics brewing in the core generates vast numbers of subatomic particles called neutrinos. The total energy carried by these little neutrinos is almost beyond reason. In a fraction of a second, they carry away 100 times as much energy as the sun will produce over its entire lifetime. That's an incredible amount of energy. Now, these little beasties are seriously elusive and hate to interact with normal matter. One single neutrino could pass through trillions of kilometers of lead without even noticing. But so many are created in the core collapse and material barreling down on the core so dense that a huge number of them are absorbed. This vast wave of neutrinos slams into the oncoming material like a bullet train hitting a slice of warm butter. The material stops its infall, reverses course, and blasts outward. The star explodes. It explodes. This is called a supernova, and it is one of the most violent and terrifying events the universe can offer. An entire star tears itself to shreds, and the expanding gas blasts outward at 10% the speed of light. The energy released is so huge, they can be seen literally halfway across the universe. They outshine all the stars in the rest of the galaxy combined. The expanding material, called the supernova remnant, forms fantastic shapes. The most famous is the Crab Nebula, from a star we saw blow up in the year 1054. The tendrils form as the material expands into the gas and dust that surrounded the progenitor star. As remnants expand and age, they become more tenuous. Some have bright rims as they push into material between the stars. Others form complex webs of filaments. I'm often asked if there are any stars near enough to hurt us when they explode. The quick answer is no. Even though supernovae are incredibly violent, space is big. A supernova would have to be at least as close as 100 light years from us before we start feeling any real effects. The nearest star that might explode in this way is Spica in Virgo, and it's well over 100 light years away. I say might explode because it's at the lower mass limit for going supernova. It might not explode at all. Betelgeuse will certainly explode someday, but it's too far away to hurt us. We're pretty safe from this particular threat. I'll note that after all this, there is another kind of supernova involving white dwarfs, which we'll cover in our episode about binary stars. Happily, we're probably safe from them too. Breathe easy. As terrifying and dangerous as supernovae are, there's a very important aspect of them you need to know. Supernovae are capable of great destruction, but they're also critical for our own existence. When the star explodes, the gas gets so hot and is compressed so violently by the blast that it undergoes fusion, what astronomers call explosive nucleosynthesis, literally creating heavy elements explosively. New elements are produced in quantities that dwarf the Earth's mass. Calcium, phosphorus, nickel, more iron, all made in the hellish forge of the supernova heat and flung outward into the universe. It takes millennia or longer, but this material mixes with the other gas and dust clouds floating in space. Sometimes these clouds will be actively forming stars. Sometimes the collapse of the cloud to form stars may even be triggered by the supernova slamming into it. Either way, the heavy elements created in the supernova will become part of the next generation of stars and planets. Supernovae are how the majority of heavy elements in the universe are created and scattered. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all created in the heart of the titanic depth of a star. That star blew up more than 5 billion years ago, but parts of it go on in you. Today you learned that massive stars fuse heavier elements in their cores than lower mass stars. This leads
That's cool, right? So now I just want to show you one last video for this evening, and then we will begin our lecture.
The sky, we now know, is full of stars and planets. Stars are massive enough to fuse hydrogen into helium in their cores, generating energy. The heat created by that process tries to expand them, but their gravity balances that outward force, creating an equilibrium. Planets, even gas giants like Jupiter, are far too small to generate fusion. The stuff inside them resists being squeezed, so their gravity is balanced by simple gas pressure. Jupiter is only about 1% the mass needed to have fusion going on in its core. That's a pretty big gap between a big planet and a small star. It's natural to ask, what would happen if we dumped more mass onto Jupiter? Eventually, it would become a star. The pressure in its core would get high enough to initiate hydrogen fusion. But what if we stopped just short of that? What if we have an object far more massive than a planet, but not quite massive enough to become a true star? What sort of thing would we have then? What indeed? By the late 1950s, astronomers were starting to get a pretty good handle on how stars worked. The mathematical equations that govern the physical processes of fusing hydrogen into helium were being worked out and applied to what we knew from observing the stars themselves. In the 1960s, the idea that you could have a star with a minimum mass was becoming clear. If it had less than about 0.075 times the sun's mass, roughly 75 times the mass of Jupiter, it simply lacked the oomph needed to squeeze hydrogen together hard enough to generate fusion. What would such an object look like? Well, it might form like a star, collapsing from a gas cloud just like the sun did 4.6 billion years ago. But instead of turning on and becoming a star, it would simply sit there, cooling. It might start off pretty hot due to the physical forces that made it, but it couldn't sustain that heat. Like a charcoal ember, it would radiate its heat away. After a few billion years, it would be cold, black, and for all intents and purposes, dead. As people started working out what such an object would be like, they tried to come up with a name for them. These things were black and small, but the name black dwarf was already being used for another type of object. Some people called them substellar objects, but that wasn't terribly catchy. Really low mass stars are red, and these new objects would be so cool that they'd emit light in the infrared and almost nothing at all in the visible. So they're somewhere between red and black. Jill Tarter, then a young astronomer working in the field, but who later made a name for herself looking for aliens, and oh boy, we'll get to that later, dubbed them brown dwarfs. And she didn't mean it literally. Stars can't be brown, but the name stuck. Work proceeded in figuring out what brown dwarfs were like, and a lot of progress was made despite there not being any actual examples of them found. But the hunt was on. Now, as I talked about in episode 26, astronomers classify stars by their temperature. The hottest are O stars, then B stars, which are slightly cooler, down through A, F, G, K, and with the coolest stars being M. But then in 1988, astronomers found a star that was so cool it was distinct from even the M-class stars. It was the first of a new cooler class of stars, so it was given the letter L. Why L? Because there wasn't any other astronomical object that used that letter, so why not? Many more such L stars were found, but still, these weren't true brown dwarfs. These stars were massive enough to initiate fusion in their cores. Worse yet, when brown dwarfs are first born, they're very hot. They can mimic higher mass L stars for a while, looking just like them, making it hard to distinguish between the two. But then a way out was found. A low-mass brown dwarf, it was determined, would have lithium in it, whereas normal stars wouldn't. Lithium is an element, the next one in the periodic table after hydrogen and helium. It can be fused much like hydrogen can, and regular stars would quickly use up their supply of lithium when they were still young. Brown dwarfs, lighter than about 65 times the mass of Jupiter, wouldn't fuse lithium at all. Very careful observations of an object would be able to detect lithium if it were there. That would provide a test to distinguish brown dwarfs from regular stars. The lithium test isn't perfect, but it does work under a lot of circumstances. Astronomers began using it to look for actual, real brown dwarfs, and so they found one. In 1995, a group of astronomers was observing the Pleiades, a nearby cluster of stars that's visible to the naked eye. They were trying to find the faintest stars they could in the cluster to get a complete sample of its membership. The advantage of this is that the distance to the cluster was pretty well known, so a faint star in it must be very low mass. They found an oddball object, which they named Theta 1. It was very red and cool, and best of all, lithium was found in its spectrum. The best models of stellar mass showed that it had about 50 times the mass of Jupiter, or 0.05 times the mass of the sun. It was clearly substellar. Huzzah! The very first true brown dwarf had been found. At just about the same time, astronomers found that another nearby star, called Gliese 229, had an extremely faint companion. Spectra showed that it was even weirder than Theta 1. It also had lithium, and so was clearly a brown dwarf, but its spectrum showed it had methane in its atmosphere. Methane is a delicate molecule and would break down even in the mild heat of Theta 1's atmosphere. This new object, called Gliese 229b, was even cooler than Theta 1. It was looking like we needed yet another letter to classify stars, and so T-dwarfs became a thing. On a personal note, when I worked on Hubble Space Telescope, Gliese 229b was one of our camera's first targets after it was installed on Hubble in 1997. I was lucky enough to work on the spectrum we took of it, and it was freaky. It emitted almost no light in the visible part of the spectrum and rocketed up in the infrared. I'd seen a lot of stellar spectra before, but nothing like this. Remember, Gliese 229b had only been discovered 2 years before. I became so intrigued by it, I wound up studying low-mass stars and brown dwarfs for several years after. Well, it didn't take long before more brown dwarfs were found. In 2009, NASA launched the Wide Field Infrared Survey Explorer, or WISE, an orbiting observatory designed to scan the entire sky looking at infrared light. It found hundreds of brown dwarfs, and now at least 2,000 are known, with more found all the time. Some are so cool that they form yet another classification, Y dwarfs. So now we have O, B, A, F, G, K, M, L, T, and Y. You're on your own for an acronym here. So if brown dwarfs aren't brown, what color are they? Some are so cool they don't emit visible light at all, so they'd be black. You could be right over one and you wouldn't see it. But some are still warm and so give off some visible light, feeble as it might be. What color would they look? Funny thing, they might be magenta. You'd think they'd be really red because of their temperature, but it's a bit more complicated than that. Remember, they have molecules in their atmospheres that absorb specific colors of light. In some brown dwarfs, there are molecules like methane and even water, well, steam at those temperatures, that are pretty picky about what colors they absorb. Some of these molecules block more red light than blue, so that messes with their colors, making them look magenta. WISE takes pictures in the infrared, which our eyes can't see. To make pictures, astronomers map each infrared color to one our eyes can see. So an image using the shortest wavelength infrared detector is displayed as blue, the medium wavelength one green, and the longest one red. Brown dwarfs put out a lot of light in the intermediate wavelength WISE sees. So weirdly, they appear green in WISE pictures. That does make them easy to spot in those images, even when thousands of other stars are visible too. The physical nature of brown dwarfs is just as weird as you'd expect. For one thing, they have a very unusual characteristic. As they get more massive, they don't get any bigger. Usually, if you dump mass onto an object, it gets bigger. Take 2 lumps of clay and smush them together, and you get one more massive, slightly larger lump. Same with planets and stars. But brown dwarfs are different. At their cores, the density is very high, and the physics is a bit different than what you'd expect. The details are complex, but the end result is that when you add more mass to them, they actually get denser, not bigger. This effect becomes important right around the mass of Jupiter, which means that a brown dwarf, twice as massive as our biggest planet, won't actually be a whole lot bigger. So what's the difference between a small brown dwarf and a really big planet? Well, not much. Nature isn't as picky as we are about having narrowly defined borders between classes of objects. Some people say a planet forms from a disk of material around a star, growing larger as it accretes stuff, while a brown dwarf collapses directly from a cloud of gas and dust. But then you could have two objects the same mass and which look exactly the same, yet one would be a planet and one a brown dwarf, depending on how they form. That strikes me as inconvenient. Astronomers are still debating this, and it gets worse. For example, as I said before, brown dwarfs over 65 times Jupiter's mass fuse lithium. It turns out that ones more massive than about 13 times Jupiter can also fuse deuterium, an atom that's very similar to hydrogen, except it has a proton and a neutron in its nucleus. But neither of these fuses actual hydrogen, so they're not considered true stars. That's still a little arbitrary, so again, I don't make too much of a fuss about it. I think it's best not to think of them as planets or stars, but something with characteristics of both. For example, the way their atmospheres behave depends a lot on how hot they are. In some, iron is vaporized, a gas. In others, they're just cool enough that iron condenses out of the atmosphere, which means it literally rains molten iron. One more thing. The nearest star to the sun is a red dwarf called Proxima Centauri, which orbits the binary star Alpha Centauri. It's about 4.2 light years away. In 2013, astronomers announced the discovery of a binary pair of brown dwarfs called Luhmann 16. They're only 6.5 light years away and became the third closest known star system to Earth. You gotta wonder, could there be an even fainter, cooler brown dwarf closer to us? We know there's none in our solar system, even out in the Oort cloud. It would have been seen by now by one of several different sky surveys. But a light year or two out? Maybe. Is Proxima Centauri really the closest star, or will we find one even closer? It seems unlikely, but no more unlikely than the existence of brown dwarfs themselves. Maybe sometime soon we'll have to rewrite astronomy textbooks again. Today you learned that brown dwarfs are objects intermediate.
So that is pretty cool, right? So it's not physically rain, but it's the elements that's on it. So in this case, molten iron. So for the first part of this lecture, I'm gonna share it with Keynote because I have a few animations I'm gonna show you guys. So for tonight's lecture, we are going to discuss the formation and the structure of stars. So how do stars form? So now we have seen low mass stars, high mass stars, and we looked at dwarf stars, but how do they actually form? How do they come together? To ask that question, we need to cover a few points, such as what is the interstellar medium? What is making stars from the interstellar medium? Young stellar objects and protostellar disks. Stellar structure, nuclear fusion, and then how does it fit into main sequence stars? In a previous chapter, you discovered the wide range of differences within the family of stars. In this chapter, you will combine observations and hypotheses to understand how nature makes stars and learn the answers to 5 important questions. Firstly, how do astronomers study the gas and dust between the stars called the interstellar medium? Secondly, how do stars form from the interstellar medium? Thirdly, how do stars remain stable? Fourthly, how do stars make energy? And finally, why do luminosities and lifetimes of stars depend on their masses? The stars are not eternal. When you look at the sky, you see hundreds of points of light. And amazingly enough, each one, like the sun, is a tremendous nuclear fusion reactor held together by its own gravity. The stars you see tonight are the same stars your parents, grandparents, and great-grandparents saw. Stars don't change perceivably in a person's lifetime or even during all human history. but they do not last forever. Stars are born and stars die. So when we speak about formation of stars and death of stars, it's not like the Death Star in Star Wars. Fitting since this is Star Wars Day. But it is actually something more like this. How can you know what the life cycles and internal processes of stars are, given that you won't live long enough to see them evolve? And you can't see inside them. The answer lies in the methods of science. By constructing hypotheses about how nature works and then testing those hypotheses against evidence from observations, you can unravel some of nature's secrets. So I'm going to swap now to Blackboard again. When people use phrases "the vacuum of space," they reveal a common misconception that space is empty. Space is not empty. There is gas and dust between the stars, called the interstellar medium, abbreviated ISM. So right now is the Orion Nebula. So this is one of my favorite objects to look at. So with your naked eye and at visual wavelengths, we will see the constellations. So here is Orion's belt, Orion's sword, one arm, the other arm, the one leg, the other leg. But if you go into Orion's belt, the center of its belt is the Orion Nebula, my favorite object to observe, and that is a stellar nursery where stars are actually formed. So we sometimes say where stars are born. But if you look in the far infrared and you look at Orion, you will see these interstellar medium around the constellation Orion. And when we look at certain places around, such where the belt is, we will see that it's much denser, more intense where the stellar medium is located. Is everyone still awake? Okay. So how do we observe the interstellar gas and dust? One way to investigate properties of the interstellar medium is to measure its effects on the starlight that passes through it. Astronomers observe that distant stars appear fainter than they should for their distance's luminosities, so estimated from their spectral types. This effect is called interstellar excitation. Distant stars also appear redder than they should for their spectral types. For example, some distant hot O stars actually look red rather than blue. This effect is called interstellar reddening, and is a result of interstellar excitation being stronger for short wavelengths light than for long wavelengths light. In fact, the interstellar medium is nearly transparent at near infrared wavelengths, allowing astronomers to look into and through interstellar clouds that are so dense they completely block our view at visual wavelengths. Another way astronomers detect material in the interstellar medium is by observing interstellar absorption lines. In the spectra of stars, you can be sure that the interstellar absorption lines are not spectral lines of the stars themselves for several reasons. For example, some distant O stars show calcium and sodium lines, but those stars are too hot to form those lines in their own atmospheres. Those absorption lines must be produced and state by atoms located between the stars and Earth. How do nebulas form? That's a very good question, Mr. Van den Berg. So nebulas, we're going to discuss that in later chapters and in lectures specifically about nebulas. But the sweet and short is nebulas are formed by stars that went supernova, and they are also formed when stars shed their upper atmospheres into space in this fusion process of different elements. So putting those together, then they form nebula, or nebulae, the plural of it. It's a pleasure. So what actually happens is with this, we have our star, the interstellar cloud, and we have the path of blue photons, path of red photons. So through a telescope, the interstellar cloud scatters or blocks the blue photons, but red photons can pierce through the interstellar cloud, and that's why it appears more reddish. So if we look at this image right here in image B, no stars are visible through the center of Barnard 86, the black cloud. But if we look at the same object through the infrared image reveals many stars hidden behind the nebulas because the wavelengths are being blocked out. So stars through the edges of the nebula are dimmed and reddened. So because we have the blue light, and that is a broad stellar line, only narrow interstellar lines are visible, and that is being blocked by the interstellar medium. The widths of the interstellar lines also give their origin. In the atmosphere of the star, the gas is so dense that atoms collide with each other often, disturbing the electron energy levels, and so hot atoms move rapidly, producing Doppler shifts. Both of those effects broaden, so blur the spectral lines from stellar atmospheres. In contrast, much of the interstellar gas is cold, and its density is very low, typically about 1 atom per cubic centimeter, although the density can be much higher in dense clouds. Even the gas is about 1 times 10 to the power 15 times less dense than the air you breathe, because atoms in interstellar media move slowly and collide only rarely. Interstellar absorption lines are extremely narrow. Spectroscopy tells you that the abundances of elements in the interstellar medium. So about 70% of the mass of interstellar gas is hydrogen, 8% is helium, and 2% is made up of elements heavier than helium. The atoms are joined together to form molecules in the densest, coldest interstellar clouds, which are called molecular clouds. Astronomers have detected more than 150 different molecules in the interstellar medium. Almost all of the material in the interstellar medium is gas, but about 1% of the mass is made up of dust particles called interstellar dust. Studies of interstellar spectra reveal that the dust particles are composed of carbon, silicates, iron, ice, and organic compounds. Note that organic compounds are molecules based on multiple linked carbon atoms, which do not have to originate with living things. Something interesting about these molecular clouds. Some of these molecular clouds we call masers. I've spoken about masers a couple of times before. Maser is the exact same thing as laser, but instead of emitting light, it emits microwaves. Laser is light amplification by stimulation of emitted radiation. Maser is just microwave amplification. So one of these molecular clouds we observe are methanol masers, hydroxyl masers, water masers, so we know what here spectrum is. So usually when something happens in a star, some of the star's material or energy released from a star goes through these molecular clouds. The particles in these molecular clouds, especially electrons, jump to high valence orbits, so it flares up, it emits more radio waves. We can pick it up with our telescopes, and we know something is happening in that region, so we can investigate what makes the maser flare up. Details of interstellar excitation and reddening show that particles are almost all less than 1 micron in diameter. So remember, your hair is about 15 microns thick. You can expect that if interstellar gas atoms are viewed against a dark or cold background rather than in front of a hot bright background of stars, photosphere, those atoms can produce an emission spectrum. Interstellar emission lines, like absorption lines, allow astronomers to study that gas and dust between the stars. Cold, neutral hydrogen floating in space produces a prominent emission line at a wavelength that can be detected with radio telescopes. This is due to the fact that electrons and protons have tiny magnetic fields because they are charged particles that are also spinning. I heard there's a meteor shower today. Is that true? There are 2 meteor showers happening twice a year. So around now in May, it will be most prominent more closer to the end of May. And there's another one usually in August, so both of them is when we move through the tail of comets. And also remember, on the 26th of May, we will have a full lunar eclipse. So that's one thing to keep in mind. So protons and electrons spin and consequently have small magnetic fields. Because they have opposite electric charges, they have opposite magnetic fields. If they spin in the same direction, if they spin in opposite directions, the magnetic fields are parallel. As explained in the text, neutral hydrogen atoms flipping from a parallel to the antiparallel state emit radio protons with a wavelength of 21 centimeters. So, have you guys heard about the 21 centimeter wavelength before? So have you guys heard before about the cosmic microwave background radiation? Can you perhaps okay, so a few yeses, a few no's. So do you want me to explain it? So the cosmic microwave background radiation is a hydrogen radiation that emanates from interstellar media all around us. It is still energy left from the Big Bang. So that's a lecture I've done for outreach programs. That's not included in this course, but for usually outreach program where no people are studying anything, has no background in science, and just listens for interest's sake, I speak about a history of astronomy. So back in the 50s, or even earlier, back in the 1930s, an engineer working at Bell Labs called Jansky was designing new radar systems. And through his antennas, he picked up a weird signal with a wavelength of 21 centimeters. If I'm correct, 21 centimeters, that's a couple of megahertz. And he couldn't explain it, so he decided, okay, he's going to build a directional antenna and try to locate the source. So building his directional antenna, he figured out, okay, the source is not coming from Earth. It's actually coming from out in space. So he has written a paper about it, published a paper, and no one believed him. Then in the 60s, when Jansky he passed away, unfortunately. So in the 60s, when people were clearing out his office at Bell Labs, another engineer, Grote Reber, discovered his article that he has written, and he and one of his other colleagues decided, well, they're going to also build a steerable antenna and see if they can still detect what Jansky actually detected. So they built a beta steerable antenna, and they also determined that this radiation was coming from outer space. And this new antenna that they built was the first radio telescope actually built. And then they did a few more observations, a few more experiments, and then they determined, well, this is coming from the space all around us. In the same time, a few physicists, I can't remember the university they worked from, I think it was from Princeton, theorized that the Big Bang should have left a residual energy that we can still pick up, and they calculated that there should be a residual at a wavelength of 21 centimeters. And voila, there you have the cosmic microwave background radiation. And the Nobel Committee said if Carl Jansky was still alive, he probably would have received a Nobel Prize in physics for his discovery in the 1990s. Unfortunately, that is sad. So that is the beginning of radio astronomy. So radio astronomy is around now for about 70 years now. Unfortunately, that is what happens in science until someone else can prove you right. So Carl Jansky was on it. So in radio astronomy, that's something we're going to discuss in later chapters. We have a unit of measurement called a Jansky. So it was named after Carl Jansky. And just to give you an idea what a Jansky is, a Jansky is equivalent to 10 to the power minus 26 watts per square meter per hertz. So let's see if I can type it into the chat. So I've typed it into the chat, and that is a Jansky. And we, as radio astronomers, when we look at the intensity information we're getting from objects in space. We talk about its energy. So can observe it in any wavelength, so any frequency. So the power we receive from the object, we classify that in Janskis. So some of these objects, just to prove how faint it is about 3 Janskis, and that can go up all the way to a couple of million of Janskis. So the next images of our galaxy include the entire sky spread into an oval. In image A would be 21 centimeter radio observations revealed by many clouds of natural hydrogen orbiting the center of the galaxy. B, the infrared image shows the location of clouds of cold interstellar gas and dust made visible by black body radiation from dust gains. Then C, in the visual wavelength image, dense dusty clouds are silhouetted against distant stars. And D, the X-ray image showed the location of very hot gas produced in most cases by the supernova explosions of dying stars. So here we can see the radio image of our galaxy. This is the line to the center of our galaxy. And the black hole in the middle of our galaxy is in the middle of this line. So now you can get a feel why we have different telescopes, why we look at different spectra, why we look at the entire electromagnetic spectrum and not visible light. This is the same, but now we look at infrared. So in infrared, we can see some of these interstellar gas media. And then optical, we will see the nice band of our Milky Way galaxy. So you've probably seen this when you are in a very dark place. You look up at night, you will see this band of our entire galaxy. This is an X-ray image of our entire galaxy. So the next thing we are going to discuss now are nebula. And what are nebula? This is my favorite object to observe. This is the Orion Nebula. There's Orion's belt, Orion's swords with the stellar media in between. Have you guys ever looked at the Orion Nebula before? If you have a chance someday, please look at nebula. It's extremely beautiful to watch. And do you know what this is? We've seen this image in... you need, unfortunately, a telescope to view this. So in the videos we've watched, we've seen this image. This is the Crab Nebula. So the star of the Crab Nebula went supernova in the year 10,300, right about there. And the Chinese actually documented it. And to this day, we can see the nebula it created. And then this. Any ideas what this nebula is called? You should have heard it in sci-fi movies. Yes, it's a real thing. So this nebula is called the Horsehead Nebula because it looks like a horse's head. And it is closely situated to the Orion Nebula. It's also still in the constellation of Orion. So, do you guys like nebulas? And then we have the Hourglass Nebula as well. So unfortunately, to COVID regulations, we are not allowed to have stargazing evenings. But in my original planning, I planned a stargazing evening, and I planned it for last year's students as well. But due to COVID, we are not allowed to have stargazing evenings because we are not allowed to share eyepieces. Pillars of Creation is also very pretty. So this nebula is the Hourglass Nebula. So I want to ask you guys, so what do you think a nebula is? Yes. So unfortunately, COVID ruined a few things for us. So yes, a nebula is a collection of dust, basically dust, but it is also a collection of the outer layers that stars have shed off, and also stars that went supernova. And yes, Mr. Van Bach, it's come basically down to a hydrogen cloud, and in these hydrogen clouds are where new stars are formed. So how do we classify nebula? So H2 regions are clouds of gas ionized by the ultraviolet radiation from nearby hot stars. They are often called emission nebula because the ionized hydrogen produces visible wavelength photons that make the regions glow with a characteristic pink color. If nearby stars are not hot enough to ionize the hydrogen in nebula, it may still be visible as a reflection nebula, produced when light is scattered by tiny dust particles mixed in with the gas. And then thirdly, at visual wavelengths, dark nebula are visible where dense clouds of gas and dust are silhouetted against background regions filled with stars or bright nebula. The key to understanding star formation is realizing the relation between young stars and densest parts of the interstellar medium. So in this image is a giant molecular cloud began to collapse and form stars a few million years ago, including 3 massive star clusters, visible in this image. Intense radiation outflowing gas from the hottest, most luminous of those stars is exciting some of its gases to glow as an emission nebula, and it's eating into the remaining dark molecular cloud at right and lower right. So this is NGC 346 nebula, and it's located in the small Magellanic Clouds, and it's a satellite galaxy of the Milky Way, about 60,000 parsecs, or if you convert it to light years, 200,000 light years away from Earth. Have you guys heard about the Magellanic Clouds before? So Andromeda is the closest galaxy to Earth, but there are also 2 other small galaxies called the Magellanic galaxies. So there's the large Magellanic. It's so small, the galaxy, that basically looks like a cloud. So there's the large Magellanic Cloud and the small Magellanic Cloud. In the summer, you can see them in a really dark place. If you look south just above the horizon, it basically looks like a cloud. But both of them are actually 2 small galaxies that's also close to our own galaxy. Where Andromeda is the closest galaxy to us, then we get the Magellanic Clouds. So this is a nebula inside the Magellanic Clouds. Spectra of the interstellar medium show that its chemical composition is basically the same as that of stars. By observing at far infrared and radio wavelengths, to which interstellar dust is nearly transparent, astronomers can peer inside even dense molecular clouds and find evidence that stars are forming there. In fact, the largest molecular clouds are each massive enough to make thousands of new stars. Nevertheless, such a cloud can form into stars only if the small portions of the cloud can be compressed somehow to high density and high temperature. At least 4 factors resist the compression of an interstellar gas cloud, and those factors must be overcome by gravity before star formation can begin. Before we begin with star formation, do you guys have any questions? You guys still following? Okay, so firstly, thermal energy in the gas appears as motion of the atoms and molecules. This thermal motion would make the cloud come apart if gravity were too weak to hold it together. Secondly, the interstellar medium is filled with magnetic fields. Ionized atoms having an electric charge cannot move freely through a magnetic field. Although the gas in a molecular cloud is mostly neutral, some ions are included, and that means a magnetic field can exert a force on the gas as a whole. Gravity must overcome this interstellar magnetic field to make the gas contract. Thirdly, everything in the universe rotates. As a gas cloud begins to contract, it spins more and more rapidly, just as ice skaters spin faster as they pull in their arms. This rotation can become so rapid that it resists further contraction of the cloud. Fourthly, turbulence in the interstellar medium can prevent the cloud from contracting. Many nebulae are observed to be distorted and twisted by strong turbulent currents that can prevent the cloud from contracting. Given these 4 resisting factors, it may seem surprising that any molecular clouds can contract at all. But both theory and observation suggest that such clouds can be triggered to form stars by effects as passing shock wave, sometimes just called a shock, the astronomical equivalent of a sonic boom. During such a triggering event, some regions of the large cloud can be compressed to such high densities that resisting factors can no longer effectively oppose gravity, and star formation begins. So, putting this now together in a few images that explains it. So here we have our molecular cloud, or our nebula. Here we have a shock wave in red approaches an interstellar gas cloud. The shock wave passes through and compresses the cloud. Motions in a cloud continue after the shock wave has passed. The densest parts of the cloud become gravitationally unstable. Contraction regions of gas give birth to stars. So in the summary of a computer model, an interstellar gas cloud is triggered into collapsing and forming clusters of new stars by passing shockwave. The event summarized here might span about 6 million years. Shock waves that can trigger star formation are common in the interstellar medium. For example, gas flows of several sorts produce shocks when they push into colder, denser interstellar matter. The ignition of very hot stars ionizes nearby gas and causes it to flow rapidly away, and new stars of all types seem to emit strong winds and jets while they are forming. Supernova explosions create powerful shock waves that rush through the interstellar medium. So now, in this image, we can see nebula RCW79 is a bubble of intensely hot gas about 70 light years in diameter. It was produced over the last million years as hot gas and radiation flowed away from massive hot stars near the center of the bubble. Then image B. Millions of years ago, a massive star exploded as a supernova in the upper left quarter of this image. And hot gas from that explosion is now pushing into cooler gas and causing the condensation of dust, which radiates strongly at infrared wavelengths. So here we can see dust condenses where the gas is compressed, so this line's over here. Here is new star formation triggered by compression. Here we can see location of the ancient supernova. Arc of gas compressed by shock wave from supernova, so here is that arc. And star formation is triggered by these compressions. Everyone's still following? Please interrupt me if I lose you somewhere. So a new term we are going to learn is a protostar. You can understand how low density clouds of interstellar gas might contract to become as dense as stars. But how does the cold gas become hot enough to be a star? The answer, once again, is gravity. So where does the hydrogen change into helium thing come in? So that is in a star when you fuse two hydrogen atoms to make a helium atom. But we're going to discuss that in the life cycle of how stars produce energy. But before we can discuss how a star produces energy, we first need to figure out how a star is formed. To see how gravity can heat the gas, shift your attention to one dense cloud core destined to become a single star. Once that small cloud of gas begins to contract, gravity causes the atoms to fall towards the center, gaining speed as they go. Astronomers refer to this early stage in the formation of star as free-fall collapse. By the time the atoms has fallen most of the way to the center of the cloud, they are traveling rapidly. The atoms begin to collide with one another and convert their inward motion to jumbled random motion of thermal energy, causing the temperature of the gas to increase. When a contracting core becomes hot enough, it produces short wavelength radiation to which the core is not transparent. Then the core's thermal energy can no longer escape, and it enters a new stage of slow rather than free-fall contraction. Although the term is used rather loosely by astronomers, a protostar can be defined as a stellar mass object that is compressed and hot enough to be opaque to radiation it is emitting internally, but not yet compressed and hot enough to be able to generate energy by nuclear fusion, as with a main sequence star. Instead, a protostar shines with energy released gravitationally from a combination of matter falling inward to the protostar plus sheer slow contraction of the protostar itself. The protostar continues growing deep inside a surrounding cloud of gas, dusty gas. Those enveloping clouds have been called cocoons because they hide the forming protostar from view. This HR diagram has been extended to very low temperatures to show systematically the contraction of a dim cool protostar. Protostars are normally invisible at visual wavelengths because they are cool objects and are deep inside clouds of gas, but they are detectable at infrared wavelengths. So here we can see a protostar's glow in the infrared. So here we can see the temperature. So now a protostar begins as an invisible concentration of cold gas deep inside a cloud. So contracting protostars grows hotter, but it's hidden inside its dusty cocoon and is detectable only in the infrared. So when it starts moving outside of its cocoon, it becomes hot enough, the newborn star becomes visible as it blows its dust cocoon away, and fusion reaction continues. Protostars are not easy to observe. Astronomers calculate that a protostar stage is less than 1% of the lifetime of a star like the Sun. And although that is a long time in human terms, you cannot expect to catch many stars in a protostar stage. Furthermore, protostars form deep inside clouds of dusty gas that block your view at visible wavelengths. And being cooler than full-fledged stars, they produce radiation primarily at longer wavelengths. Astronomers must therefore depend on observations at infrared and radio wavelengths to search for protostars in the natural environment. At the center of the Orion Nebula, also known as Messier 42, before I continue, are you guys familiar with Messier objects? So to explain Messier objects. So Messier objects are 110 astronomical objects, and they were catalogued by the French astronomer Charles Messier. And that happened in the segment between 1771 and 1774. So he started and he looked through his telescope, and if he looked at an object, he started as Messier object 1 and he categorized 110 objects. So each year there's a competition going on that states if you can photograph all 110 Messier objects in one night. So some of these objects are visible just after sunset and some is visible just before sunrise. So you have to know exactly where these objects are, and your timing must be perfect, and you need to photograph them through your telescope. If you miss one object or struggle to find one object, then you won't have enough time to go through all of them, and you will also miss the opportunity to view some of these objects while they are setting. So each year there are these Messier objects. So the Orion Nebula, my favorite object, is also known as Messier 42. So Messier 42 lie 4 brilliant blue, white O and B stars known as the trapezium. The most luminous in a cluster are a few hundred stars. Surrounding those stars are the glowing filaments of nebula, more than 8 parsecs across. Like a great thundercloud illuminated within, the churning currents of gas and dust suggest immense power. The significance of the Orion Nebula lies hidden, figuratively and literally, behind the visible nebula. The region is ripe with star formation. Note 4 important points. The visible nebula is only a small part of a vast dusty molecular cloud. You see the nebula because the larger stars born within it have ionized the gas and driven it outward, breaking out of the molecular cloud. Visual and infrared observations reveal small dusty clouds of gas called Bok globules that may be in a process of forming stars. A single very hot and short-lived O star, one of the stars in a trapezium cluster, is almost entirely responsible for producing the ultraviolet photons that ionize the gas and make the nebula glow. The star is so massive that it has already become a main sequence star, while its smaller siblings are still protostars. Infrared observations reveal clear evidence of active star formation deeper in the molecular cloud behind the visible nebula. Many of the young stars in the Orion Nebula are surrounded by disks of gas and dust. So I'm just going to check where we are. Just going to check where we are on the slides and where we are doing with time. We can do a few more slides. So due to this movement of ions, light is produced. Yeah, not really light. You can see it through radio telescopes because it causes a magnetic field. Remember, when you have moving ions, you have moving electrons. Moving ions and electrons causes a magnetic field to occur. Depending on the object itself, the magnetic field can then radiate in a part of the electromagnetic spectrum depending on its energy, and that can range from visible light all the way up to gamma rays and all the way down to radio waves. Does that answer your question? Yes, so that's exactly what's happening. Pleasure. So, contagious star formation. Not only can astronomers locate evidence of star formation, but they also have found evidence that star formation can stimulate more star formation. If a gas cloud produces massive stars, those massive stars ionize the gas nearby and drive it away. Where the intense radiation and hot gas pushes into surrounding gas, it can compress the gas and trigger more star formation. Like a brush fire moving through the interstellar medium, star formation can spread itself especially by the actions of massive stars. And astronomers have located such signs of such episodes. Star forming region N11b. So in image A, the blast of light and ultraviolet radiation from the formation of an earlier generation of stars compressed neighboring gas clouds and triggered the formation of the stars at the left side of the frame, so over here. Those stars are now triggering the birth of a third generation of stars at the right. Those stars are now triggering the birth of third generation stars. Note that the Bloch globule at the upper right. So this is the Bloch globule. Then in image B, compression can trigger the formation of very massive star clusters. Superstar cluster Westerland 1 contains approximately 500,000 stars, some extremely massive. It must have formed no more than 5 million years ago. So here we can see massive stars in this region were triggered into formation by compression from the formation of earlier stars out of the image to the left. Here we can see new stars are forming in these dense clouds because of compression from the stars to the left, so compression from them. If we lived inside this monster cluster, Earth's sky would contain hundreds of stars brighter than the moon. If that is something mind-blowing. The history of star formation in a constellation of Orion is written in the stars. Judging from the luminosities and estimated masses of the most prominent examples, the stars at Orion's west shoulder are less than 12 million years old, while the stars in Orion's belt are almost 8 million years old. The stars of the trapezium at the center of the Great Nebula are no more than 2 million years. Star formation has swept across Orion from northwest to southeast, apparently beginning near Orion's west shoulder. The massive stars that formed there probably triggered the formation of other stars in Orion's belt. That star formation episode may then have caused the formation of the new stars you see today in the Great Nebula. So you guys are getting quite a feel why I like the Orion Nebula and why it's one of my favorite objects. So here we can see what's happening. This is the viewpoint to Earth. Here are a few protostars, the hot trapezium, molecular cloud, and this is just the artist's representation. So this expanding ionized hydrogen from the hot trapezium stars are causing other stars such as the protostars to form. When most of the material in a protostar's cocoon has fallen inward or been driven away, the protostar will no longer be quite so hidden. The locations in the HR diagram of protostars that have become detectable at visible wavelengths because their cocoons has disappeared is called the birth line. Once a star crosses the birth line and becomes visible, it continues to contract and move towards the main sequence at a pace that depends on its mass. Stars in this late stage of formation, are sometimes called young stellar objects, or pre-main sequence stars. I prefer the term young stellar objects to distinguish them from earlier protostellar stages. The more massive a star, the stronger its gravity, and therefore the more rapid will be its contraction. Astronomers calculate that the Sun took about 30 million years from when its cloud began contracting until it became a main sequence star. But a 30 solar mass star would take only 30,000 years. A 0.2 solar mass star needs as much as 1 billion years to finish forming and reach the main sequence. As a contracting molecular cloud core becomes a protostar, the cloud rotates faster and faster. The rapidly spinning core of the cloud must flatten into a spinning disk like a blob of pizza dough spun into the air. Gas from the envelope that has lost some of its orbital velocity through collisions can shrink directly to the center of the cloud, where the protostar grows more massive. Surrounded by the disk, other infalling material can add to the disk and then move within the disk plane towards the star. So in this image, we can see the more massive a protostar is, the faster it contracts. A 1 solar mass star requires 30 million years to reach the main sequence. The dashed line is the birth line, so this is the birth line of these stars. Where contracting protostars first become visible as they dissipate their surrounding clouds of gas and dust, so they're cocoons. So here we can see a 15 solar mass star will take 0.16 million years, 5 solar mass 0.7 million, 2 solar mass 8 million, 1 solar mass our sun 30 million, 0.5 solar mass 100 million. So you guys are still following. So I think we're going to end off tonight's lecture with this slide. And that's the formation of a protostellar disk. So here we can see a slowly rotating cloud of gas begins to contract. Conservation of angular momentum spins the cloud faster and flattens it. And that forms into a growing protostar at the center of the rotating disk of gas. And that's how a protostar is formed, and then in essence how a star is formed. So ladies and gentlemen, I think we're going to call it the evening. I will remain active if you have a few more questions. Otherwise, you're more than welcome to log off. Good luck with your semester tests tomorrow, and good luck with everything else. If I'm not mistaken, next week is recess, so I will probably see you guys the week after next week. You have an off-topic theoretical question. If there was a planet exactly like Earth with human life technology on it, what's the furthest distance from us that could be from us for us to be able to observe it and prove that there's life on it? So the last chapter we're going to discuss in this module is life out there. So it all depends on how close those objects are. So you've probably heard about the Fermi paradox. If you haven't heard about the Fermi paradox, please read up about it. But if there's a different planet with life on it, the best way we can detect it is by seeing if they generate electromagnetic radiation. So electromagnetic radiation travels at a speed of light towards Earth. So the closest they are, so say for example, our closest star Alpha Centauri, it takes light to reach, is 4.2 light years away, so meaning if there were a planet that supports life and they have technology, it takes those electromagnetic radiation to reach us 4.2 years. We on Earth have been using electronics and electricity for basically 150 years. So we've been generating electromagnetic energy from Earth for the last 150 years, so meaning we have reached a bubble around Earth of 150 light years. So it all depends on how far that planet is away. Yes, that can also be it. There's a chance that their light is millions of years ago. Or they are now in the Stone Ages, for example, and it's going to take that light millions of years still to reach us. But read up about the Fermi paradox. I think that is going to blow your mind. So I'm going to stop the recording.